Hello and welcome to our second online workshop within Trace project. I'm glad to see how much interest our project raised, considering the large participation to the first edition last week, when we had more than 100 participants. Right now, we are almost 60 persons into this meeting, and I'm sure that the number will increase shortly. I will start this session with a brief recap for those who participated in the first workshop, which can also be considered an overview of the TRACE project for those joining us now for the first time. So Tracing Climate Change, shortly named TRACE, is a collaborative project involving 3 European universities: the University of Bucharest, the National and Capodistrian University of Athens, and Aix-Marseille University, together with an educational organization from Greece, E3STEM. The project is funded by European Union through the Erasmus Plus programs. The primary aim of TRACE is to provide students and educators in the field of geosciences with high quality educational resources based on real field data documenting geomorphological evidence on climate change. The educational materials were developed using data collecting during fieldworks conducted by each partner university. These fieldworks included photographical materials, field measurements, sedimentary analysis, topographic survey, and geomorphological mapping. All these data sets were integrated with relevant bibliographic information on isostatic and tectonic movements, climate change, sea level fluctuation, and their geomorphological indicators across diverse environmental settings. As a result, a comprehensive library of educational resources has been created, including video presentation, lecture notes, database, and also data querying applications, virtual field trips, story maps, quizzes, interactive exercises, and much more. All these were designed to support engaging and effective learning experiences. These resources are freely available to the general public via the eGarnet platform, an open e-class platform that can be accessed after creating a personal account. A step-by-step guide for accessing the platform is available in the resources section of the project website. I already put the website of the project into the chat section, so you can access results section of this web page in order to understand how can you access the educational material provided by this project. In addition, each partner university has to organize a series of online workshops aimed to promote these educational materials and also to facilitate their understanding through direct interaction with the experts who develop them. This is why we are doing right now. Each workshop series addressed topics related to formation, evolution, and dynamics of landforms in coastal and deltaic environments, but not only, across the participating countries, with a strong focus on the impact of climate change. The workshops highlight the role of paleoshorelines, coastal morphology, tectonic movements, and climate driven processes in shaping present day landscapes. More broadly, they provide participants with the tools needed to interpret the imprint of climate change on the environment, while also offering the opportunity to explore new landscapes and compare similar geomorphological formation across different geological contexts. To recap, during the first workshop last week, we introduced the main geomorphic landscapes analyzed within TRACE project. Coastal environments were examined through the lens of their dominant dynamic factors, namely waves and currents, illustrated by processes such as coastal erosion, sediment transport, shoreline retreat, and storm impacts. In contrast, mountain environments were approached in terms of their capacity to preserve mountain permafrost, exemplified by features such as rock glaciers, freeze-thaw process, slope instability, and hydrological changes, highlighting permafrost as a key indicator of climate variability. Moving forward, the theme of second workshop, of today's workshop, is reading the past, reconstructing ancient landscapes to predict the future. Our first speaker is my colleague, Dr. Alfred Vresmeanu-Stroie, professor of physical geography at the University of Bucharest Faculty of Geography. He is also the head of Sfântu Gheorghe Marine and Fluvial Research Station and of the GeoDar Research Center of Geomorphology, Geoarchaeology, and Paleoenvironments. Over the past few years, Professor Vresmeanu-Stroie has been actively involved in several major research projects related to climate change, including Climaland, which investigates the response of climate-sensitive environments in the Carpathians and Danube Delta to global warming and sea level rise, and also Chronocarp, a project focused on climate and tectonics-related surface processes in southern Carpathians and northern Balkan mountains. Today, his presentation focuses on coastal lagunal environments using Ialova as a case study of paleogeographical evolution. Alfred, you have the floor.
Thank you, Michu. Good evening to everybody. So we'll have half an hour full of water, of coastal water. We'll have a talk, which I will split in two parts. The first is more theoretical, but I hope to be interesting. It's short and about the coastal lagoons, especially morphology, sedimentology, stratigraphy. And the second part will be a study case of our joint research project made in Peloponnese, in a coastal lagoon. Okay, so I will share the screen. Hey, Michu, can you confirm that it's visible for you now, the PowerPoint?
Yes, we can see the presentation. We can hear you well, so everything is okay.
Perfect. Okay, so first of all, it's important to understand what is a lagoon and how it looks, what it consists, which processes are shaping, and we'll start with the fact that they are widely present on the world coast. Approximately 13% of the total shoreline are hosting coastal lagoons, and they formed relatively recent. Most of them are created between 7,000 to 4,000 years ago. So they are created, all of them, during the mid-Holocene period, and were established due to the rising sea levels within Holocene marine transgression, when the lowermost part of the coast were flooded by the seawaters. And after that, the waves, especially via longshore currents, succeeded to block these embayments with coastal barriers, to close them and to transform in coastal lagoons. So they are typically present on gently sloping coastal plains. And very important is the fact that most lagoons, in fact, host river deltas. Here it's an, I think, a preconception of us to consider completely different environments, the deltas and the lagoons, but in fact, small river deltas are usually present within the coastal lagoons because most of them have relatively relevant, important watersheds, and these watersheds are creating rivers strong enough to build deltaic lobes within the lagoons. So the difference between the large river deltas that you know from personal experience or from literature and these small deltas created within lagoons, it's about size, it's about the quantity of sediments that they have. So having this in mind, we may go further now to discuss about stratigraphy and the elements which compose an barrier lagoon system. So we have 3 or 4 main elements composing. Each time we have a coastal barrier which is closing the lagoon. It should be composed of sands or of gravels, and sometimes are mixed sediments, a combination of sands and gravels in the same matrix. Then it is the lagoon by itself. Otherwise, it is directly an estuary, so it's the drowned valley which has been blocked by the longshore currents. Doesn't matter. It's also a lagoon. So please, especially for the Romanian audience, don't pay too much attention at this discrimination between the lagoon and limans. In fact, limans are another type of lagoons. It's not completely different. It's just a subtype. But I will come back in a few minutes to give more details about the limans. So we have the lagoon like another element. Then we have this young coastal plain. In fact, it's a delta plain we have, but it's an optional. So not all of the lagoons have coastal deltas inside, but most of them they have. That's why I wrote here on the position number 3 that the late Holocene coastal delta plain are usually present, but optional feature. And then there are the inlets which in most cases in the world are maintained by the tidal currents, by the tides, but also by the waves, especially during the storms, because the storms may break the barriers and induce large variability in the sea level position due to the storm surge and then to the depression after the storm surge. Okay, otherwise, the sedimentology of these main units, it's very discordant. That's why using drills and boreholes, we may discriminate easily each fascia specific to each unit because the coastal barrier fishes is composed by a coarse matrix, very well sorted. Doesn't matter if it is sands or gravels or a mixture of them. Otherwise, the lagoon deposits all the time are very fine sediments, especially organic rich muds, clays and silts all together with a poor sorting of them. And the inlets are usually much coarser than the barrier due to the capacity of the tide or wave currents, and it's also easily to discriminate in a stratigraphy. And we have in this, this is the coastal barrier, the lagoon, tidal flats, and very important another feature which is underrepresented in the Mediterranean because we have just small tides. So we can develop here a tidal delta, which is completely different by a river delta because all the sediments that are developing this tidal delta are carried on by the tidal currents with a flat tide delta within the lagoon and an ebb tidal delta in the sea. So depending on the tidal currents direction. Otherwise, in terms of hydraulic connectivity, we have this classification of Kierve, which is very simple with three main cases, main types, depending on the degree of connectivity. If it's a weak one with just a single narrow inlet, we might call it choked lagoons, and they become much more dominated by the wind in terms of water circulation within the lagoon. Otherwise are the restricted lagoons with two or more stable inlets, and the leaky lagoons, which have several wide inlets and have a very active water exchange with a neighbor ocean or neighbor sea. And then, depending on the evolutionary stage, is this three type framework with an useful stage when the lagoon system consists into an open marine embayment or a flooded valley, which we call it Ria Valley. Then the coastal barrier creates and closes that setting and transforms it in a proper lagoon. And after this moment, the main process will be the filling with sediment, the sedimentation, which cover partially the coastal lagoon. And barrier subtypes closing the lagoon. Usually they are barrier islands. It's a very popular settings in front of the passive coastal margin of the river deltas. Otherwise are barrier spits, which are still open at an end member, like it became the Sakhalin in this case. We have bimouth barriers closing the embayments, and we may discuss again about this Liman subtype. So Liman, it's an Slavic or Russian word. It's very popular, used in the Black Sea, and this happens because the Black Sea level history is relatively different in comparison with the Old Ocean. It's much more dynamic because in 90% of the time, the Black Sea was disconnected by the Mediterranean, by the World Ocean, and this is why the sea level history in the Black Sea was much more rapid, much more dynamic. And for most of times, the Black Sea level was very low positioned, like between 80 and 110, 120 meters below current position. And this is why the valleys coming from different directions succeeded to cut a deep valley. It's the case of the Kasimcha. If you think Kasimcha has a very large lagoon in front, it's a liman, it's the Tashaul liman, and it's also available for the Dniester, Dnieper, Don. So all this valley, which in the present have the contact with the Black Sea via Ria Valley, blocked by a barrier that is called liman. So in this subtype of lagoon, this type of liman, it happens to be even open waters in the present because their valleys are so deep that even to present they didn't succeed to create a large enough delta to fill all this liman. But of course, this should happen in the future, in the next millennia, if the sea level will remain relatively constant, which is not the case anyway. So you may see here in the right panel the presence of this liman type, even for the Dniester, Dnieper, Bug, the several books here. So, but in the same time, with a detail for the Dniester, you may see the formation of the river delta within the liman here. So one point that I insist for you is to be more mobile and to accept the fact that these lagoons comprise sometimes liman type lagoons, and usually they also have deltas within developing inside. So don't consider distinct categories all the time, but they mix, they join. Now we'll start the second part of the presentation, which will be a study case for the Voidokilia-Yalova coastal lagoon system. That's why even the title I put here is not just about the lagoon, it's a coastal lagoon system, and even a delta will be present in our discussion. You'll see, so we are in the southwest part of the Peloponnese, is the wettest region of the Peloponnese. Here, this is important because the vegetation is a little different, greener, denser. In the same times, the river carry more sediments than other Peloponnese rivers and succeeded, how you could already see in the image, to create an delta plain here, transformed in a coastal alluvial plain. Is this one and this one. So we'll see in another image a tentative reconstruction in time, and you'll see how it developed. Otherwise, this coastal area, it's very interestingly in terms of tectonics, as long as we are close by the Hellenic Trench, so at just 50 kilometers offshore, it's one of the deepest part of the Mediterranean Sea, deeper than 5,000 meters. It's shaken by several earthquakes. This is one of the reasons that the researchers suppose that this lagoon system was affected by tsunami induced by earthquakes. And one of the reasons of our study, it was to intercept this tsunami signature in the lagunar sediments and then trying to date as good as possible. And we'll discuss about them immediately. In terms of lithology, you may see the presence of a limestone barrier, which is a limestone ridge closing all the systems, and then behind was an active bay filled partly with these deltaic systems. Okay, this is how it looks in the present. It's an image photograph taken to the north from the Navarino castle. You may see this beautiful omega bay shaped here with a barrier dividing the Voidochilia embayment by the Ialova lagoon, and then even farther to the east or to the north, we have the coastal plain, in fact, delta plain transformed in a coastal plain. Okay, now I will show you the position of the corings that we performed in 2 campaigns here. Finally, there are 4 corings. Call it VDK from Voidochilia 1, 2, 3, 4. The position we have at the contact between the barrier and the lagoon for VDK 1 and 3, while 2 and 4 were placed distal. The strategy was to have an image of the stratigraphy close by the seaward position of the lagoon to intercept, also to have information about the coastal barrier formation and development, and the other one were further inland in order to intercept the Xerxes-Lagados delta plain, delta formation, and tsunami signature, because if a storm in the best scenario may affect the proximal part of the barrier, a tsunami is supposed to be strong enough to completely flood all the lagoon and to affect the salinity and to let also a signature in the sedimentology, in the stratigraphy. That's why we need usually distal position for the tsunami signature. You may see here the stratigraphy that I will discuss shortly for you. All of the boreholes have the basal part composed of coarse units. How you read this kind of diagrams? First of all, you look at the width of the symbols. The wider they are, the coarser the fraction is. And the color, it's about the gravel, sands, or fine sediments. So we use yellow for the sand. This means medium, or this means finer if it's narrower. And orange, it's for a combination of sands and gravel. So the presence of the gravels in the sandy matrix is colored in brownish orange, like this one. Otherwise, the gray and narrow symbols are for the fine sediments representing muds. It's if there are very, very fine, like the clays, we use it black. If it's clay or silty clay, will be this kind of gray. So you may see that all of the boreholes in the basal part have coarse sediments. This means that we intercepted in each position the former embayment, so the position of the coastal embayment, which was active before the creation of the barriers and the formation of the lagoon. Immediately after the Voidochilea barrier inception, the former embayment transformed in the lagoon. That's why the energy of the environment decreased suddenly, and you may see this beautiful contact between coarse and fine sediments which appear here, a different position, and represents the transition from the embayment to the lagoonal deposition. We have an exception for this core, for the VDK2. You may see also that vertically the contact is with a few meters above. It's not like usually between 7 and 8. It's around 4.5 meters here. And this is induced by the Xerxes river mouth presence in this part, which after that was artificially moved here. So this happened in the 20th century, but formerly it created a delta in this position. So we intercepted here a delta front creation, which is a little different. Keep in mind that we are in progress with this study, so we're still waiting for around 35, so close by 40 new carbon-14 ages that we want to obtain here. Maybe are too many, but I think when we are speaking about tsunami, it's very important to know exactly when they happened. And this is why we are a little obsessed to have as good age depth models as possible. And also for the paleogeomorphological reconstruction, I think it's very important to know all the details concerning the sedimentology to see if there are hiatuses, if there are periods with higher sedimentation, which may be related by the wetter climate episodes in the Peloponnese. So if you really want to have new good results, you need also a good resolution of your study. That's why we will have plenty of datings still waiting for these boreholes, and also we'll have some OSL datings. So we'll have 6 OSL datings which are in Szeged laboratory for this unit here on VDK2, because it's a good opportunity to find the formation of this delta here. But we also got the first OSL results, and you may see this this position, which we'll use, which is very convergent with this one, saying that somewhere between 6.4 kiloyears and 5.9 kiloyears was the transition between the embayment and lagoon, was the timing of the barrier formation, in fact. Okay, let's speak a little about the paleo-tsunami imprint in this lagoon. We are using VDK 2 and 4, just remember, and we already have the results for one core, VDK 2, where we are trying to use at least 3 proxies to reconstruct tsunami. One, it is the grain size, so the sedimentological signature, which means that a tsunami will bring in the lagoon some coarser sediments and poorer sorted. And if you are looking here at the sorting expressed in phi units, you may see that we have some poorer sediments in these 2 positions, and also the mean size larger with some sand presence in this. So this is a first indication. The other one, it's about the carbonate. It's inorganic carbonate presence, which we represent with the magenta unit. Normally, the carbonate are suddenly increase in the tsunamic layers, and you may see that we have a rapid increase in the carbonates here and here. So this is convergent with the poorer sorting that we got. Then we have the geochemistry, because this borehole was scanned by ITRAX at Orchova Research Station, and we used some geochemical ratio. The most important concerns the presence of calcium and bromium normalized by titanium. And you may see this increase both for calcium iron ratio and for strontium potassium here and here. So this is another indication geochemically that probably we have a tsunami imprint there, but the most robust proof that we may use when are looking for paleo-tsunami is the microfauna, especially the presence of the forams of the marine microfauna in the lagoon, and if possible with some species which are specific to the mid and lower shelf position, which are usually living at a big depth. And you may see that around 4.5 meters depth, we have a transition from a marine salty environment to a brackish to freshwater, because the marine taxa disappear and appear instead the Cypridae storosa, different types of Candona, like Candona neglecta and Candona angulata or Pseudocandona, which are specific to freshwater or slightly brackish, and especially this freshwater alga, Charophyta, which you could see also suddenly appear here. That we know that around 4,000 years ago, something changed dramatically in terms of water salinity in the Yalova Lagoon. We'll discuss immediately what could happen to change the salinity. And from this moment, every pulse of saline water should be related by a marine invasion. And yes, it's true. You may see these two blue horizon that we plotted here with the reappearance of the Ammonia beccari forams, and also of the Chiteromorpha and Loxoconcha ostracot species, which are specific to the very salty waters, and which are correspond with a decrease in freshwater Candona and freshwater Charophyta. So these two depths are completely coincident with the depths where we recorded high carbonates, poorer sorted sediments, and the geochemical ratio specific to marine invasion. That's why we are almost sure that we intercepted at least two paleo-tsunami, that we are still waiting for defining their time span, their chronology. And for the last part of the presentation, we'll speak more about geomorphology. We'll speak, for instance, about this beautiful Omega Bay. So we already know that the barrier was formed 6,000 years ago, but of course at that moment was very teeny, was just a beach ridge. This beach ridge, we suppose that enlarged with the progradation of another 3-4 beach ridges, but anyway, giving in fact that the wave energy within Omega Bay is a low one, because we have this relatively narrow entrance. Also, the beach is narrow, so it's like a 5, 8, 10 meters width beach. So 3 or 4 beach ridges will cover finally no more than 60, 80 meters. But in the present, the coastal barrier has more than 300 meters. And this is induced not by waves, how some researchers believed in the past, but by winds, because we have here beautiful parabolic systems. We can call it also elongated parabolic dunes developing from northwest to the southeast. And it's not a coincidence that the widest area of the barrier is positioned in the southern extremity of the barrier, because here will be in correspondence with the storm winds and also with the inlet, which allows for more exposure, for a greater wind power. And of course, this is a normal geomorphologic supposition that we tested via some potential eolian sand transport models. And here we have the works of Freiberger, 79, which developed some equation for estimate the sand mobilization in the deserts using only wind values. And using his equations, we obtained the drift potential and the resultant drift potential and the resultant drift direction. So we used the values of winds modeled in front of the Voidochilia beach, bay, and we got this nice sand rows where the red line, red arrow, represents the resultant drift direction, and the length represents the strength of the transport. So this is a clear mathematical demonstration that the parabolic dune systems, which is developed in the southern part of the Voidochilia barrier, is coincident with the resultant drift potential obtained using wind values. Okay, so this is an active aeolian system developed in the last millennia, which succeeded to transport sand from the beach and from the ford dunes far away within the lagoon and to create these sandy aeolian lobes here. So it's completely aeolian feature, and even this part, it's in fact aeolian, but much smaller because the wind blowing from the west or from the west-southwest, it's much less than from the northwest. Okay, and the last thing that I would like to present to you is the evolutionary model that we are working. So it's in progress because we still need good H-depth model to refine some unit, but it's like 80-90% already. So somewhere around 7 millennia before, we have this bay behind the limestone barrier. So everything was flooded by seawaters. Then, around 6,000 years, the Voidochilia barrier was created. It was a narrow one, or skeletal, but was created. We know from the boreholes that we have here in the proximity, and in the same times, the Sersalagados rivers and other smaller rivers started to create their river deltas within this bay. Then around 4,000 years, when the Voidochilia barrier enlarged, in the same time here was created another barrier which succeeded to close the Yalova or to disconnect Yalova lagoon from Navarino Bay. We know this from microfauna data because it's the moment then the water salinity decrease significantly, and this happens just because the connectivity was interrupted. And have in mind that this barrier doesn't appear like from nowhere. It appeared in this position because it's like an here this lagoon was in fact geomorphologically like an delta subaqueous platform. So was with shallow water and here deeper water, and exactly at this contact between the delta front and the subaqueous delta terrace platform, this barrier could create in the Navarino Bay. And this is the present morphology with this very beautiful aeolian feature in this position. So this is the model. We still refine, but more or less this is. So yeah, 30 minutes. I'm perfect. Thank you. I'm happy to have questions.
Thank you, Alfred. You were just in time. It was very interesting to see how complex could be these lagunal systems, and also how challenging could be the terminology, considering the linguistic differences between countries. So, even though we are just in time with the schedule, you could ask a few questions. we have 1 or 2 minutes to address questions if you have it. Otherwise, you can use chat anytime in order to address questions or to write some comments and so on. We will have a short section of discussion also at the end of this workshop, so you still have the opportunity to take the mic. Otherwise, let's go to the next speaker, who is also a colleague of mine at the University of Bucharest, Dr. Florin Tătui, associate professor at the Faculty of Geography and also researcher at the Sfântu Gheorghe Marine and Fluvial Research Station, and also researcher at the Research Institute of University of Bucharest. He holds a PhD in physical geography from the University of Bucharest and received advanced training at Utrecht University and University of Copenhagen. Dr. Tătui is affiliated with numerous international scientific organizations and currently serves as president of Romanian Association of Geomorphologists. He has been actively involved in many national and international research projects as a principal investigator, as partner coordinator, or research team member. His lecture today is entitled Delta at Risk, the example of Danube Delta. Florin, you have the floor.
Thank you, Mihaela. I hope you can hear me. Thank you for the introduction. Yeah, I'm in Brussels now. My internet connection is not so good. So please, if you lose me, please text me on WhatsApp. Yeah, just to tell me if something happens. I hope not. Yeah, because the internet connection is not so good, I will also stop the camera. And yeah, can you see my presentation?
Yes, we can see it now. We can hear you well. I will keep you up to date if something is changed.
Yes, thanks a lot. Yeah, this is a comprehensive, let's say, presentation related to deltas at risk with a focus on the Danube Delta. Last time I was 50 minutes, so today I will try to stick in the 30 minutes. So the main outline for today's presentation is related to a general overview of the delta. The first 3 chapters are related to the definition of deltas, also why they are important and what are the key which are, let's say, inducing lots of stress in world's deltas. And then the last 4 chapters will be dedicated to the Danube Delta, which is very important not only for Romania but also for the entire Europe. So first of all, what is a delta? Of course, we are talking about a low-lying landform, which is shaped by the deposition of sediments coming from a river. These sediments are slowing down when they enter into a sea, in our case, and they are losing their transport capacity, and they are accumulating. And a delta, as you can see here in the right hand side, has let's say 2 main parts. The subaerial delta is the part that we can see, and an important part is represented by the underwater or subaqueous delta, the part that we do not see. There are 3 main types of delta depending on the main driving factor. So the processes that are mainly driving the formation of the delta in a particular time in its evolution, because you'll see that there are many changes in delta life. We have the river dominated deltas, where the river is the most important agent. So the river transports sufficient sediments in order to counteract the wave action and to deposit these sediments into the sea. The second type is related to the tide dominated deltas, where the tidal processes are the most important. The tide dominated deltas they are not present, let's say, in the Black Sea and Mediterranean basins, which are covered by the partners of our consortium in the TRACE project, and the wave-dominated deltas, with a smooth arc line which is shaped by the wave energy. So the waves are the most important um, driver, and the wave-induced processes are successful, let's say, in moving the sediments coming from the river along shore and depositing shore. Yeah, most of the deltas in the world started to form, let's say, in the last 8,000 years, and especially in the last 6,500 years, when the sea level started to stabilize, and we can identify three main phases in the delta development. The first phase is this bayhead aggradation, when the river starts to infill some former bays into the sea, and here we have the earliest human occupation in deltas. The second phase is a phase of expansion of the deltas. So we have lots of sediment going into the sea, and we have progresses of both aggradation, so sediment deposition, vertical sediment deposition, and also progradation, so the increase in the surface of deltas. And this is the period where between 6.5 and 2 kilo years before present. It's the period when we have significant growth in human occupation of deltas. And the third phase in the last 2000 years is a phase of progradation with large-scale human occupation and many modification of the deltas. Of course, increasing this human impact, especially, let's say, in the last 100 years. Here we have a global distribution of deltas. There are not the whole, let's say, all the deltas worldwide, but here are depicted only the most important ones. And you can see we have many deltas, and of course we speak about 700 major deltas worldwide, and they are inhabited by 350 to 500 million people, so 4 to 6% of the global population. But of course 40% of global population lives within 100 kilometers from these deltas. So there is let's say a high impact of humans on the deltas if we speak about these numbers, but also there is a high vulnerability of these social systems if we speak about threats related to deltas, and you will see in a couple of minutes this. Also, 10 of the all 34 megacities of the world are in deltas. So we have lots of vulnerability here, especially with climate change, especially with the sea level rise. And you can see here some examples of the most important deltas of the world: Ganges, Brahmaputra, Amazon, Nile, Mississippi, and of course the Danube, the most important delta in Europe. Why are deltas important? They are important firstly because they provide lots of ecosystem services. And we can speak about four types of ecosystem services. Some related to provisioning lots of supplies, for instance, fresh water, food, reed materials, and also drinking water for local communities. They also regulate floods, also attenuate the storm surge, so the impact of storms. They sequestrate carbon, which is really important, and also they purify water. They are also important from the cultural point of view, in terms of cultural heritage, in terms of the tourism and recreation, scientific research, and also aesthetic value. And they support different types of uh, areas related to biodiversity, migratory birds, fish, and rare endemic species. So deltas are really, really important, as you have seen, both from the socio-economic point of view, but also from the biodiversity point of view. And the problem is that we have many threats related to deltas, and these threats have two main drivers. Some of them are nature drivers, and some of them are human induced stressors. If we speak about natural hazards, of course, we speak about flooding, the riverine flooding, and also flash floods, storm surges related to different storms, cyclones, typhoons, etc. Also, subsidence because of the natural compaction of sediments, which is happening in deltas, tsunami risk, droughts, salinization, and wildfires in reed beds. But we have lots, I told you, especially in the last, let's say, 50 to 100 years, lots of human induced stressors related to sediment starvation because of construction of dams, agricultural drainage and channelization, urban expansion, land use changes, groundwater, oil, gas extraction, which drive subsidence in different types of the umbrella which is represented by the climate change amplifying all these threats. And I will go quickly to some of these threats in order to understand a little bit the big picture. Yeah, the humans are let's say the main problem now in these deltas, because they are inducing lots of problems. And you can see here the expansion of population in deltas after 1975. You can see in 1975 we had a total population living in deltas of let's say 150 million people, and now we have, let's say, around 400 million people, so 3 times increase. And of course, the highest increase is represented by the Asian deltas. You can see them here. Yeah, what are the humans doing? They are starting to change the landscape, to change the environment. And in the upper plot, in plot A, we can see the percent of anthropogenic area, so the area transformed in terms of land use changes. And you can see in the Asian deltas, also in the Nile, Rhine, Rhone, Po deltas, percents, let's say, higher than 70% of anthropogenic area. And this anthropogenic area comes mainly from agriculture. You can see in plot C these yellow areas for Ganges, Brahmaputra, Rhine, Meuse, Mekong, or built up areas. So all types of cities, villages, or other types of infrastructure. Here there is a nice example, let's say, example in Var, where we have an airport land reclamation. So lots of people living in deltas, and they change the landscape. We have lots of land use changes, and the natural area is less and less present in most of the world's deltas. Here we have an example from the Mekong, showing the main drivers in italic, and also the main consequences in bold of these changes. So we talked about sediment starvation. Of course, this is because of the construction of dams. We have all types of land use changes, and we are speaking here about agriculture. For agriculture, we need a lot of water, so we have groundwater extraction, and this um, produces land subsidence. So aside from the natural land subsidence caused by sediment compaction, we have this, let's say, more important land subsidence, which is caused by groundwater extraction and by oil and gas extraction. If we, for instance, about the Mississippi Delta. We also have sand mining, uh, flooding, population growth and urbanization, as you have seen, especially in the Asian deltas, and with the global sea level rise. This means surface saline intrusion, coastal flooding, coastal erosion, and also saltwater intrusion, which increases the vulnerability of coastal population, also the vulnerability of, let's say, different types of ecosystems. And if we talk about saline intrusion and saltwater intrusion, we speak also about changes in species, in different type of species in the deltas. And here are some results related to land subsidence and sea level rise in global deltas. There is a very recent paper published in Nature, and in the right hand side picture we can see that some of the Asian deltas, Yellow, Pearl, Brantas, Irrawaddy, Ganges, Mekong, they are characterized by both sea level rise, higher sea level rise, let's say more than half a centimeter per year, but also higher, very high subsidence rates, especially from caused by the groundwater extraction. We can see here the 95 percentile, for instance, for yellow is something like 5 centimeters per year um, subsidence, and this causes threat to, let's say, a few hundreds of thousands of people in these deltas. And here is the global distribution of delta area and population below the mean sea level. So the people which are below mean sea level mean uh, people and areas mean that they are highly vulnerable in the next decades. And yeah, just a few examples: Mekong, Ganges, Red River in Godavari, also in Asia, the Nile Delta and the Rhine in Nile in Africa, Rhine in Europe, and Mississippi in North America. So this means, yeah, of course, lots of risks in the next decades, and yeah, money to be invested in order to cope with these risks. One problem that we talked, I presented to you earlier, is related to this diminishing fluvial sediment supply. And here are two nice plots from an article of Sivitsky in 2021. As you can see, the fluvial supply dropped by 50% in the Anthropocene, so in the last 50 years. So this means that the global rivers are transporting only half of the sediments that they transported 50 to 70 years ago. This means that most of the deltas are sediment starved, as we call them, so they cannot fight against the wave action, and most of them are either eroding or are flooded by sea level rise, and also flooded by different storms. also related to this damming of the rivers, we have a lower sediment connectivity. So when we have a higher sediment connectivity, this means that the sediments are moving slowly from the springs to the big rivers and to the sea in the end. But if the connectivity if we have higher fragmentation of these rivers, the connectivity is less and less important. So this means that most of the sediments are not going into the sea anymore. And here is a nice example from a paper of Grill and collaborators, where we can see that we have this degree of fragmentation for almost 70% of the global rivers. And the result is in the right hand side pictures from an article of Manon Besset 2019, where we see lots of red. Red means erosion. So delta vulnerability levels means deltas with retreating shorelines. And most of the deltas, you see, they have the highest degree of vulnerability 4. So this means that they are eroding very, very fast. If we want to see the big picture, of course, we have the global mean sea level rise, which is nowadays is 3.6, 3.7 millimeters per year, and continuing to increase exponentially. Let's say with a projected 1 meter by 2100, but this is only the absolute sea level rise. When we add the subsidence, and you have seen that the subsidence could be very, very important in some deltas, we reach 1 to 3 centimeters per year local subsidence, which of course is very, very high. And we have also this sediment deficit of 50 to 90% because of the sediment trapping behind the upstream dams. So this means that delta building slows or stops, or even we have lots of erosion, lots of land loss. So this was, let's say, the big picture related to which are the main problems. Of course, there are others also, but we do not have time to speak about this. The main problems that are affecting deltas worldwide. And now I will go to a case study related to the Danube Delta, where our coastal research group from University of Bucharest, let's say, does research for almost 30 years. Next year we will have, this year or next year we will have 30 years of research there. So the Danube Delta is located in Romania, most of it, and Ukraine on the Black Sea coast. This is the area of, let's say, 5,800 square kilometers. It has the highest level of protection, UNESCO Biosphere Reserve, Ramsar Wetland, World Heritage Site. It has 3 main arms and a fluvial discharge of 6,500 cubic meters per second. In terms of biodiversity, you see it's a hotspot of biodiversity, not only for Europe, but also for the world, and is the world's largest compact reed bed. So very big delta, very important from the biodiversity point of view. And you can see here some examples. Part of the delta, which we call the fluvial delta, is this one with many lakes, and the images below are from the maritime delta, which is this one, where we also have an influence. In terms of, let's say, wave energy, the significant wave height is almost to 1 meter. The waves are coming mainly from the northeastern direction, and they are inducing on most of the Danube Delta a longshore sediment transport directed to the south. So most of the sediments are moving from north to south. And of course, we have this distribution with sands mainly up to 5 to 7 meter depth. And afterwards, we have very fine sediments related to silts and the clays. It's a, let's say, general sediment distribution in front of the deltas. And now we will speak about some vulnerability related to Danube Delta, erosion, subsidence, and sea level rise. And here are three time-lapse examples from the Kilia Delta, which is the northernmost part and which was prograding, let's say, for almost 300 years until the 1960s, 1970s. And today we can see we see retreat of the shoreline. You can also see the construction of barrier islands and then spits, and we see this movement of sediment along shore and the straightening of the shoreline. These are clear signs that this part is eroding. So we have lots of problems, and in order to understand the erosion, we have to speak about the main drivers. And of course, when we speak a delta, we speak about, let's say, a battle between two contrasting forces. One is related to storms, which through waves redistribute sediments along shore, and of course some of the sediments are moving offshore, so they are creating erosion. And the floods, which are constructing, so the river comes with sediments which build up new land in deltas. And this is of course an ongoing process in the vicinity of river mouths. And if we want, let's say, to understand easily this, for instance, for the Danube Delta, this is a sketch made by my colleague Florin Zăinescu. The Danube Delta, we have water coming from the floods, 1 million Olympic swimming pools, coming with 100,000 trucks full of sediment. So this is the river. And we have the storms with 1 million waves, summing an energy on the scale of an atomic bomb, which means a few megatons TNT. So these are the two contrasting forces, and depending on the balance between them, we have either construction of new land if the river is more important, or we have the destruction, so the erosion if the waves are more important, so the storms. And we looked about this for the last 150 years. We are very lucky that we have some maps from 1856 made by the European Commission of the Danubes, so we could track what happened in this 100, now it's 170 years. And this is the Danube Delta coast, and you can see here that, let's say, for 1 century we had lots of areas prograding, especially in Kilia. This green, of course, we also had some erosion, but the accumulation processes were, let's say, more important. Nowadays, so after 1979, we see lots of red along the Danube Delta coast, so lots of erosion, even in this area, which was, I told you, advancing for 250 years. Nowadays, we see lots of erosion, and I showed you the time-lapse images depicting this erosion. If we look at underwater, so at the subaqueous delta, the underwater delta, we see the same pattern. So in the second half of the 19th century, we had rates of change of almost 6 centimeters per year. You have to see this as vertical accretion, and then up to 8 centimeters per year, and afterwards, let's say at the mid 20th century, and now you see almost zero. So we do not have sufficient sediments to construct neither the underwater part of the deltas nor the subaerial part, so the delta plain, and these sediments are eroding now. And the main factor is represented by the fact that the Danube is not carrying sufficient sediments anymore. If we look at this graph and at these numbers, we can see that nowadays the Danube is carrying 1/3, so 30% of the sediments that used to carry 150 years ago. And this is related to the number of dams. This is the number of dams built only in Romania. And you can see that after 1960s, we had more than 200 dams on Danube distributaries only in Romania, and this caused the sharp decrease, which we can also see for different periods related to different time steps that we used in our studies. In terms of storminess, so in terms of wave power, wave action, wave energy, uh, things are not so bad, let's say. Here we have different proxies, storminess index, a storm severity index, and also the wave power with different colors. And we can see that, of course, we had a period between 1960s and 1980s with higher energy, so more frequent and more intense storms. But nowadays we see this decrease in terms of wave energy, and this is related to climate variability. And here it's a synthetic graph putting everything together. So the let's say 2D, the horizontal development of the delta, which is here, in comparison with what storminess did, and also QS is the sediment discharge of the Danube. And what we can see that let's say from 1850s to 1950s, we had this expansion of the delta related to low storminess and high sediment discharge. Then we had moderate storminess and still high sediment discharge until the 60s. Then we had higher storminess and low sediment discharge, and the accumulation processes were so the erosional processes started to become more and more important. And nowadays, even if we have low to moderate storminess, we have lots of erosion because of the fact that we have very low sediment transport of the Danube. And some of the consequences we can see easily. We talked about this Kilia Delta. This is the development. So from let's say 1750 to 1970s, we see this explosion, let's say, this expansion of the delta. And after the 60s, the 70s, we see that we have erosion even in this area. And comparing these two maps, let's say one map and one aerial image from 1856 and from the present, we can see that the Kilia lobe switched from a river-dominated lobe, as you can see here in 1856, to a wave-dominated lobe here, where the waves are the most important driver. Also, another consequence is related to the deflection of river mouths. Here is an example from a southernmost branch from Sfântu Gheorghe mouth. Also a comparative image between 1857 and 2010. And here is the position of the middle part of the river mouth. And we see that it moved slowly, especially in the 20th century. It moved slowly to the south. So this means that the longshore sediment transport coming from north to south is more important than the fluvial current. So the mouth is slowly deflected to the south, and is another consequence of this low sediment discharge. Also, humans are present in this equation because at the main navigable channel of the Danube, the Sulina, we have these jetties, as you can see here, which are blocking the longshore sediment transport, and of course they are inducing higher erosional rates to the south. Related to the last three decades, so you have seen before this analysis, let's say long-term analysis on more than 1.5 century. What we did is using satellite images and deriving water lines from this satellite image to explain the shoreline changes in the last 3 decades. And here with yellow we have different shorelines in the last 30 years extracted from the satellite image, and from these shorelines we can obtain this kind of graphs with seasonal dynamics and also the multi-annual trend. And on the uppermost graphs we can see erosion with rates around 3 meters per year, and there are other places with accumulation, yeah, up to 3 meters per year. But when we sum everything up, so this is a synthetic graph, in the middle we can see the average change rate in meters per year for the after 1992, and we can see lots of erosion on the whole Danube Delta coast. So nowadays, let's say 70% of the Danube Delta coast is retreating, as you can see here, with rates reaching up to 10 meters per year here between Sulina and Sfântu Gheorghe. And on the rightmost part, we can see a Hofmöller diagram. Red means erosion, gray means accumulation, and we have lots of erosion. And this erosion started to cover larger areas nowadays. In terms of subsidence, unfortunately, we do not have so many data. So we need a better estimation. Here are just an example from the European Ground Motion Service, where we can see that the natural, let's say, subsidence is somewhere around 1 to 1.5 millimeters per year, caused mainly by the sediment compaction. In terms of sea level rise, this is an example from Copernicus for the whole Black Sea. The trend is lower than the world ocean, 1.2 plus minus 0.8 millimeters per year. But we also have other problems related to pollution, eutrophication, yeah. And here we can see some examples with algal blooms either in the Black Sea or in the Danube Delta lakes. What is coming to the future? Yeah, of course, the news are not so encouraging. We predict plus 1.2 degrees Celsius warming, more frequent extreme precipitation, and even if, yeah, the data show that, let's say, the multi-proxy wave climate for the Danube Delta coast is encouraging, let's say with less storms and let's say lower intensity. Also the sea level rise, as you here is the absolute sea level rise is not so high. The problem is that we do not have enough sediments. We also have this kind of engineering structures, and what is worse is that there is no sediment management from dams to coast in order to better manage all the sediments on this chain. And possibly this is something we are working now, some changes in the dominant wind direction. This could lead to extension and intensification of erosional processes in the future. And of course, what can we learn from this? That we have many compound risks in the deltas and also in the Danube Delta. These compound risks are related either from nature factors or from human-induced factors. So the one risk analysis should integrate all these compound risks. We should promote more the nature-based solutions in especially for this sediment restoration and sediment management. Of course, local communities should be the central part in these management actions. We should increase the connectivity that I told you is now very, very fragmented for most of the rivers. And of course, from our point of view, from scientists, we need monitoring, and long-term ecological and hydrological delta are irreplaceable. Okay, these are the main conclusions. Thank you very much. If you have questions, please.
Thank you, Florin, for this presentation, which allow us to understand how important are deltas as a product of land-sea relationship, but also how fragile could be to human impact. If you have questions, please do not hesitate to address. We have a question on chat. Which GIS-based tools are most suitable for analyzing and highlighting erosion processes in deltaic environments? Florin, can you answer now, or you
Yes,
should?
yes. Yeah, I can answer now. So we are using, for instance, we are using some general tools like the CoastSat, which is freely available, where you can download different kind of, let's say, shorelines derived from satellite images. But you can also use some your own in-house, let's say, made algorithms, and we used one related to automatic water extraction index. If someone is, let's say, interested about this, you can write me an email and I can give you, let's say, more details about this.
Correct me
Because
if
I
I'm
don't
wrong.
think we have time now to.
Florin, correct me if I'm wrong, but as far as I know, there are there is a database on EGANet platform accessing from
Yes.
through CoastSat.
Yeah. For CoastSat on EGANnet, if you connect to EGANnet platform, there is an exercise there with a Python using CoastSat, and you can learn how to get these automatic extracted shorelines from satellite images.
So, Alexandru, you should access the EGANet platform in order to have access to this data base and also to this app to use to data query. Okay. Do you have any questions? Other questions? You still have the chat in order to address questions if you discover that are interested in some topics more. Otherwise, let's go further. Last but not least, I'm pleased to share the floor with Dr. Anna Carcani, a member of laboratory teaching staff at the Faculty of Geology and Geoenvironment at the National and Kapodistrian University of Athens. She holds a master diploma in oceanography and management of marine environment, while her doctoral research focused on the geomorphological and environmental evolution of coastal zone of central Cyclades. Dr. Carcani's research interests include geomorphology, coastal geomorphology, natural hazards, paleogeography, and sea level change. She has participated in numerous research programs, including Erasmus+, bilateral Greece-France projects, Interreg Med, FP7, and Coast Actions. Today, she will present Naxos on Move, how tectonics and climate reshape a coast. This presentation is focused on the paleogeographical evolution of Naxos Island. So, Anna, you have the floor.
Thank you, Michaela. Good afternoon, everybody. So I will share my screen to make sure that everything is working.
We can see your presentation. Perfect.
Perfect. So today I will talk about Naxos Island. Let's have a look at where it is to help everybody. So the presentation is basically a compilation of different work that our team has done during the several years or maybe decades, I would say, on the island of Naxos. Just to give you an idea, Naxos is located in the central of the Aegean Sea, where you see this red square, and it's basically the largest island on the Cyclades. Cyclades are, as you can see, in the center of the Aegean Sea. And if you have a look also in the map on the right, we can see that they are considered by a relatively calm seismic area, while the surrounding area is generally characterized by high seismic activity. So overall, and if you have a look at the literature, you will find that most Cycladic islands are considered to be affected by gradual subsidence, which is related to the crustal thinning in an extensional tectonic regime. But we will talk about more of this during this presentation. So this is the background that we need to keep in mind. Let's have a better look at Naxos Island to give you an idea. So if you look at both maps, and if we have a look especially at the relief map, you can see that Naxos relief is mountainous. There is a central mountain range running from the north to the southern end, and we have a maximum altitude of about 1,000 meters, located more or less in the center of the mountain range, and it's actually the highest point in the Cycladic area. As if you notice, the relief is more intense in the north and the eastern half of the island, where we have steeper slopes and deep valleys. But if we look at the western part of the island, it is generally characterized by very mild relief. And basically, the main plains of Naxos Island can be found there. And this is actually the area that we will focus also today. So if you look on the map here, we can see that the dominant part of Naxos is composed by marbles and schists. And on the western part, we can find neogene and quaternary sediments. And we have an extensive outcrop of granodiorite. So basically, the lithology of Naxos is consisted of various lithological formations. They have a different resistance in erosion, and in combination with the river network and tectonics have basically shaped the present-day morphology. On the left part of the slide, you can have a look at some geomorphological maps of the western part of Naxos. This is actually the area that we will focus on. And actually, the main characteristic is, especially on the western part, we have a lot of depositional processes, and we find exceptional coastal dunes, lagoons, tombolos, as well as underwater beach rocks. And all of these features are almost continuously found along the western part of Naxos. And we will see about that a little bit later as well. But let's try to see a little bit how the recent geological history of Naxos is. Here you can see basically how the area of the Cyclades was approximately 20,000 years ago during the last glacial maximum, when the sea level was about 120 meters lower than today. So you can see that many of the Cycladic islands were united into a large island, and Of course, Naxos and Paros with the rest of the islands were already joined. If we move a little bit closer to the present day and we have a look at this map about 14,000 years ago, again, we can see that still Naxos is not as we see it today, but it was still united with Paros Island and the surrounding islands as well. Here we can see the same area, 12,000, approximately 12,000 years ago, when the sea level was about 43 meters lower. Imagine that Paros and Naxos Island, these two islands that you see in the center, became separated at around 8,000 years ago. So a lot of the coastal features that we see today in Naxos are geologic, if we look at the geological time, are very, very recent. And this is the area as it is today. So what I want to share with you in the next slides is basically a compilation of different researches that has been undertaken by our team during several years, where we investigated paleogeography and coastal changes on Naxos Island. We focused on different features like sediment corings, beach rocks, as well as tidal notches, and a combination in the end of all of this in order to also try to estimate the relative sea level changes in the area. So we will first focus on sea level, on the paleogeographic evolution of this very nice area that you see here. And as you've already heard also from the first presentation by Alfred, coastal wetlands and lagoons, these type of environments are very vulnerable environments, and they can offer us a very powerful tool to understand the changes that have taken place over the past few thousand years. So by studying the sediment, the stratigraphy in such environments, we can find information about sea level changes, about climatic changes, about human interventions, because all of these are recorded in the sediments of coastal marshes, wetlands, and coastal lagoons. So we have the accumulation of sediments and organic material over time that gives us a very detailed record that we can study and unravel the evolution of a particular area. So let's, I will give you a brief overview of how we actually work. So we essentially did a number of shallow sediment corings, where you can see here on the map on the left part. So here. For the area of Agios Georgios that I will show you right now, we took 3 cores. They reached the maximum depth of about 5 meters. And the lab analysis, you can see the steps in a way on this slide. So the work included recording of the stratigraphy, analysis of the paleontology, analysis of the different granulometry of the sediments, and of course, dating of our findings by using radiocarbon dating. Then all of this information is synthesized in order to end up with the paleogeography of the airport lagoon. So this is the area that we are going to focus for now, where you see this red square. And here we can see some of the main results of the stratigraphic analysis and the paleontological analysis. So in fact, the analysis of the sediments in combination with the microfauna that were found inside the 3 cores that you can see on this slide showed that during the studied period, we're talking about more or less the last 6,000 years, parts of the western coastal zone of Naxos and Agios Georgios in this fact were active lagoons, and they were we will see the details in the next slide. So here you can see the paleogeographic reconstruction of Agios Georgios area. Here you can see the area as it is today, and here on the left you can see the area as it was at about 6,000 years ago. So today the area is a wetland, but 6,000 years ago it looks like it was a lagoon. And let's have a better look here. So you can see here on the top part, again, a paleogeographic map of the area around 6,000 years ago, and on the lower part you can see the area as it is today. Based on the findings of the corings, the present day area, which is known as the airport lagoon. Let me show you also. So this area here, it looks like it was the ancient harbor of Naxos. And what we can see here with the different letterings, they are in Greek, but I will explain to you in any case. So with the letter A here, we can see the formation of a tombolo at the airport lagoon. Here on the letter B, we can see a reef that it's composed of beach rocks, slightly submerged beach rocks. They reach down to a depth of about 2 meters. And these actually beach rocks represent fossilized shorelines of about 1,500 years ago. Today, these beach rocks basically protect the coast from erosion due to the wave action. And on the area Gamma or C, what you see here, this area seems like it used to be a harbor. Based on our findings, it looks like it was an active lagoon from about 6,000 years ago until quite recently. And it probably served an ancient area of that time, which is right here, where you see the letter D, which is called Iria. So these are the findings that we had based on the corings that we did in this area. And now I'm going to take you to another site. We are looking at a site slightly southern of Agios Georgios. So we are on this site here. This site is called Mikri Vigla. In terms of analysis, a similar process took place also in the area of Vigla. And the 3 yellow arrows that you see here are basically the location of the 3 sediment corings that took place. As you can see also the landscape here in this area, this area is characterized by a low land morphology. There are some torrents of temporary flow. We have the coastal lagoon, we have the dunes in front of the lagoon, and we have some underwater beach rocks as well in this area. So on the lower part of this slide, you can see the 3 corings that we performed on Mikri Vigla, along with the paleontological results. And on the top part, you can see the paleogeographic reconstruction of this area. Here on the right, you see the area as it is today. You can also note the location of the 3 sediment corings. And on the left, you can see the area as it used to be 3,000 years ago. So this continuous line that you see here basically represents a beach rock barrier. And where the white arrows point here, they show a part of the beach rock that was subsiding periodically, allowing the entrance of seawater into the Gulf. And if you have a look also on the inland section of the 2 maps, we can see that the hydrographic network 3,000 years ago, it probably discharged in the Vigla Bay, while today we can see that part of this network has migrated to the southeast. We can understand from both of these case studies that Vigla area was protected, like Agios Georgios Bay, by this beach rock bench. And based on our findings, we consider that at least during the Bronze Age, so roughly 3,300 years BC, Vigla may have also been a place where boats could anchor. But now let's move to another landform that is very, very frequent on the western part of Naxos. I've already mentioned beach rocks. In Naxos Island, the beach rocks are quite extensive and very, we find them very frequently on the coastal zone. If you have a look On the map here on the left, I can zoom a little bit for you to see a little bit better. We can see that we have a lot of sites with beach rocks present. So we investigated all of these sites. Here you can see some relevant photos as well. And what we actually did for the study of the beach rocks, most of the beach rocks are found below sea level, reaching about 6 or 6.5 meters below the present sea level. So we did a detailed spatial mapping of the submerged beach rock slabs by underwater geomorphological mapping, but also by using a UAV. We collected beach rock samples in order to examine the cement, but we also collected samples in order to use them for luminescence dating. So you can see some of the thin sections on the lower part of this slide, and here you can see the 7 beach rock samples that we dated using luminescence dating, OSL. Here you can see a very characteristic aerial view of the submerged beach rock slabs at Naxos Island. This is the site of Plaka in Western Naxos. We will talk more about this site. On average, 3 or even 4 slabs. When I'm saying slabs, I mean distinct places where we find beach rocks well developed. So we found either 3 or 4 slabs in each site, and these slabs can reach a maximum depth of about 6.5 meters. And most of the shallower beach rocks are found near sea level, more or less. So based on the analysis that I've mentioned that we did, we were able to talk a little bit about the coastal zone evolution in several sites. I chose to focus here on Plaka area because it's a very characteristic and quite unique site in this sense. So Plaka Beach is located here. And on the satellite image, you can see the 3 different slabs that we have identified. These 3 slabs seem to have very well recorded the morphological configuration of the coastline during the last 4,500 years ago, based on our OSL datings. If you notice the yellow lines that are presented here, the yellow polygons, we can see that these submarine beach rocks can be followed parallel to the modern coastline for more than 2 kilometers, more or less. We can identify, if we look also on the satellite image, we can find 3 paleoshore lines. And if you have a look also on this second paleoshore line, we can notice that it's quite similar to the geometric shape of the modern coastline. But if we have a look on the northern part of Plaka Beach, we can see that the orientation of this part of the beach rock is not exactly parallel to the present-day coastline, but it appears rather different. It seems to end up here in this circle, which is a shallow outcrop of granodiorite. And this morphological configuration may indicate that the geomorphology of this coastal area was different, with the presence of paleotombolo in the past, and probably the existence of 2 bays due to the presence of this granodioritic outcrop. You can see 2 maps here where you can see the paleogeographic evolution of this area as well. On the top map, you see how the area is today. On the lower map, you see how we estimate that the area used to look like approximately 4,500 years ago. But we also find other landforms that can give us information about the coastal evolution of Naxos Island. So another important coastal landform that we find in Naxos, but also in surrounding islands, are what we call tidal notches. Tidal notches are these features that you see here, like this one or the lower one here. So they are undercuttings. They can be a few centimeters to several meters deep, and they are commonly cut in steep calcareous cliffs at the sea level, at the mean sea level. And based on research that has been done both in Naxos but also in surrounding islands, as you can see also from the map here, at least 7 former paleoshore lines were identified, reaching a maximum depth of about 280 centimeters. By combining basically the morphology of the submerged notches, the seismicity of the area, and by correlating the findings with archaeological information, Evel Pidu and her colleagues found that there were rapid subsidence events that took place, that they were most probably of seismic origin. There is a shallower paleo shoreline at about 30 to 50 to 40 centimeters that was found both on Naxos but also on other Cycladic islands, that was attributed to the recent global sea level rise, and at least partly by a relatively recent earthquake that took place in Amorgos Island, which is here, in 1956. And the deeper shorelines that you can see also in this sketch on the lower part were considered to be connected to repeated subsidence events and not due to gradual subsidence. This information can derive from the profile of the tidal notches, and this is one of the reasons why they are very, very useful to understand coastal changes and relative sea level changes in different areas. And by actually correlating these paleoshore lines with archaeological information, but also with the sediment corings that I showed you before, Evel Pidu and her colleagues dated the deeper notch at 2.8 meters at about 3,300 years before present. And in this sense, they were able to estimate a subsidence rate of about 0.9 to 0.8 to 0.9 millimeters per year. By combining all of this information that I've described in the previous slides, you can also see here a summary plot of relative sea level changes that derived from the work we did in Naxos, but also from the work we did on Paros Island, using the beach rocks, some archaeological information, as well as the sediment corings. And we can see that, let me give you some graphs as well. We can see that based on the data, we had a relative sea level rise by 2 meters during the last 2,000 years, and by at least 3.9 meters since 4,500 years before present. What we actually try to do is, you can see in the plot that we have these two lines. These are modeled curves from 2 glacial isostatic adjustment models, and they can be used to try to estimate based on the mismatch between the models and our observations, we can calculate basically average rates of tectonic subsidence. And based on our findings, we have found that we have an average tectonic subsidence of about 1 millimeter per year since 5,500 years BP. And it does not seem to have been constant during the late Holocene. But in any case, if we look at all of the data, we can see and we can understand that the subsidence trend on Naxos Island, but in general also in the central Cyclades, is most likely a combination of seismic events, as suggested by the tidal notches, and by gradual long-term subsidence due to the location of these areas in an extensional structural pattern. But why does this matter when we're talking about climates, change and all of this. If we look at the present day sea level trends, or if we look at the trends for the future, you can see here results from different IPCC reports and calculations of or predictions for the global mean sea level in the future. And we can see that the future paints a somewhat worrying picture in a sense. Depending if we look at the most optimistic, the moderate, or the pessimistic scenario, we have an estimate that sea level rise can reach 40 centimeters or even 80 centimeters by 2100. In each case, we are talking about sites like these that can be brought that will be threatened, and the current and the future climate crisis and the rising sea levels basically are a significant risk for environments like the ones I'm showing you here on Naxos Island, for sure in other sites, but we're focusing on Naxos. And in fact, the tectonic subsidence adds to the rate of the sea level rise. So this means that the risk of flooding and erosion is actually exacerbated. One very characteristic case is that, as I mentioned, along the entire western coast of Naxos, we have the presence of these well-developed sand dunes in front of coastal lagoons, as you can see in this picture. And you can see a similar picture here. So this is the site called Agios Prokopios, where we can see again that we have these dunes, the lagoon, and then the landward part of Naxos. And what you can see from this profile also is that here are the dunes and here is the lagoon. Many of the lagoons are lying below the sea level, actually. So what do the dunes do? The dunes are actually protecting the landward part from flooding. And this is the case in many different sites on the western part of Naxos. Here, for instance, we can see a similar cross-section from another site in Glyfada, a little bit further to the south. Again, we see the same pattern. We have dunes protecting the landward part from flooding. And again, here you can see different cross sections. This is from the site of Plaka that I've showed you before with the beach rocks. Here you can notice that we don't have any coastal lagoons, but in some areas we have some well-developed dunes that are protecting the landward part. What you see here is an image from 2021. What you see here is the same site from one of the sections, more or less one month ago. So we had a storm that struck the area, and it caused severe damage on the coastal area, and you can notice it here on the different photographs. There was a storm surge that happened, but at the same time, part of the underwater beach rocks were removed from the underwater area because they wanted to make sure that tourists could enter into the sea. You can see that there is the development of this road here, and also we have buildings built on the dunes. All of this is a combination of what led to the result that we see here. So when we talk about climate change and sea level rise, we have to also take into account the human interventions and the impact that they can have when we're trying to see what will happen in the future. So we need to take all of this into account. Keep in our mind what has happened in the past so we can understand the tendency of the area, but also seeing what's happening today and what we expect to happen in the future. Thank you for your attention.
Thank you very much, Anna, for the presentation. Your example on how tectonics and sea level oscillation can contribute to drawing the shorelines is greatly appreciated, especially when it comes from Naxos, which can be considered an open laboratory for geomorphology and geology classes.
Exactly.
So thank you very much.
Thank you.
Students, if you have questions, it is time to address them, not only to Dr. Anna Carcani, but also to previous speakers. Let's say we still have few minutes left, even though it's sharp 8. Maybe we should tell students that every year in Naxos Island, National and Kapodistrian University of Athens organize a very interesting educational program for students across Europe, especially for the Civis Alliance, but not only. So if you are interested to find more about this environment, you should apply. You could find the information on Civis Alliance web.
And a new is coming very soon. It will be
Yes.
announced, I think, somewhere in June.
Yes, at the end of June and
Yeah.
start of July. So no questions, no comments, or you are too shy to address them. I also wrote all the social media pages of our project, so please follow us if you want to stay updated with the news about this project. Otherwise, if you have no other intervention, I will thank you very much for your attention, for your presence here with us, and see you in 2 weeks from now, considering that the fact next week all the Orthodox are in holiday, in Easter holiday. I will take the opportunity to wish happy Easter holiday for those who celebrate these days. So see you in 2 weeks from now. Thank you very much. Bye
Thank you.
bye.
Bye.
Bye. Have a good evening.